And now before that, we state an important result, so-called Dini result, Dini theorem. If for some delta in 0 pi, we have 0 pi phi u over u is finite, then s and x goes to s. Okay. Why this is true? This is this is delta. This is just another expression of this theorem. Because if this is true, the proof, if 0 delta phi u over u is finite by Riemann lemma, we know that 0 delta phi u over u sine n plus half of u du goes to 0 as n goes to infinity. Of course, you can add 1 over pi in front of this. Then, by the previous theorem, our previous theorem says that if this integral goes to 0, then s and x goes to s. Okay, so according to this theorem, we know that by the previous, we know that s and x goes to s, proving our this Dini theorem. Dini is Italian mathematician. Okay, so but the Dini theorem also involved unknown s, because of the s appears in the expression of phi u. So this is also not very convenient for application. So we hope to determine whether the Fourier series converge using only information about our function f itself. Okay, so to this end, we have the following result. If f satisfies the Holder condition, Holder condition of order alpha. Alpha is a number in 0 and 1. What this means? What is the Holder condition of order alpha? That is, there exists a delta positive and L positive such that for u in 0 delta, we have fx plus u minus fx plus not greater than Lu alpha, and fx minus u minus fx minus also not greater than Lu alpha. Here, the fx plus and fx minus is the one-side limit of f at the point x. Here, fu plus is the limit. X plus. X plus is the limit of x goes to, not x, maybe use t. T goes to x from the right. And fx minus is the one-side limit for t goes to x minus. That is put on the left. Okay. So of course, in this case, we require that the function f has one-side limit at x. The left limit and the right limit are all exist. If f has one-side limits at point x and satisfies the whole condition of order alpha, this condition we will denote it by h alpha. Okay, so f satisfies h alpha. Here alpha is a number, positive number not greater than 1. So under this condition, the conclusion is that then the Fourier series of f converge to fx plus fx minus over 2. The average of f at the point x, the average of the one-side limits of f at the point x. Or we can write that is the Fourier series ak cosine kx plus bk sine kx equal the mean value of the one-side limit at the point. So we know that the Fourier series converge under what condition? Once f satisfies all the condition of order alpha. Okay, all the condition of order alpha means that fx plus u minus the one-side limit not greater than u alpha for u in a small neighborhood of 0. Okay, so if f satisfies all the condition, then the partial sum of the Fourier series at the point x converge to the mean value of the one-side limits of f at x. In other words, the sum of the series is precisely the mean value of the one-side limits. Okay. So the proof of this theorem is not difficult. I will prove this later. But I just want to point out that in the statement of this theorem, we do not mention the unknown s. Actually, this is our s. The mean value of the one-side limit is our s. Okay. So s is known. We just checked for the mean value of the one-side limit. Now we prove this theorem. The proof of this theorem is having the preparation before. It is not very difficult. We see that phi u over u is, we take s. To write phi u, you have to given the s, we take s to be the mean value of the one-side limit. Then phi u over u is fx plus u plus fx minus u minus fx plus fx minus a half. But this is s, and we need to minus 2s. That is the definition of phi, and then over u. This is just fx plus u minus fx plus over u plus fx minus u minus fx minus over u. Okay, so since f satisfies the whole condition, that is fx plus u minus fx plus less than L u alpha. And also, this is also true for minus and the left limit for u in the small interval. We see that this term, as a function of u, this term is absolutely integrable in 0 delta. Fx plus u minus fu plus x plus over u du will not greater than 0 delta L u1 minus alpha du. This is finite. This integral converge. This integral has a singularity at 0, but because 1 minus alpha is less than 1, so we know that this integral with singularity converge. So similarly, the integral of the second integral x minus u minus fx minus over u also converge. Therefore, we conclude that cu over u du converge. Okay, now from this theorem, this theorem tells us that if the integral of phi over u is finite, that is, the integral converge, or in other words, phi over u is absolutely integrable, then s and x goes to s. Okay, so now we have already verified that for s is equal the mean value of the one side limits at the point x, then this integral does converge. Okay, so according to this theorem, we see that our Fourier theorem converge to the mean value of the limit. Okay, so proving this theorem. Now we have obtained this result about the convergence of Fourier series at the point x. This is very useful. Now we study some basic situation. We consider the case that f has one side derivative. So a useful remark: if f has one side derivative, that is f at the point x fx plus or in other words, and then the whole condition is satisfied. Then f will satisfy h1. H1 is whole condition of order 1. Why this is true? Because by the definition of one side derivative, so there is delta positive if h greater than 0 less than delta. Then suppose we consider the right derivative at x. So if right derivative at x exists, then by definition of limit, there is a delta positive. Once h is less than delta, we will have fx plus h minus fx h minus the one side limit is less than 1. Okay, so we see that fx plus h minus fx over h will not greater than 1 plus the absolute value of the one side limit, denoted this by L. So that is to say fx plus h minus fx less than L h, because h is positive. And here fx is the one side limit. Fx is the one side limit. F is continuous at x. Okay, f is continuous at x. So so in this case, the Fourier series of f converge at x, and the sum is exactly fx itself. Okay.